Hello, I'm David Doughty. I'm chairman of the History of Hydrology Committee of the American Geophysical Union. We're here in Boulder at the Quadrennial Assembly of the IUGG and of the IEHS, the International Association of Hydrological Sciences. As part of our oral history project, we're lucky to have here on campus Professor Mark Meier from the University of Colorado, and to interview him, Dr. Gordon Young, our newly appointed Secretary General of IEHS. Gordon, it's all yours.
Thank you, Dave. Well, Mark, it's really good to be here with you today as one glaciologist talking to another. Perhaps we could start by you telling us why you got interested in glaciology and perhaps a little bit of your academic history leading up to that point.
Well, Gordon, I'm actually quite honored to participate in this program, and especially to be interviewed by a glaciologist such as yourself, of which I have great respect. You ask how I got started. Well, it was a little devious. I started my university studies during World War II, went off to the Navy, learned electronics, came back and found out that I could get a degree in electrical engineering pretty easily. And that gave me a chance to minor in some mathematics and things like that. So I got that degree, but decided that I really liked the mountains and the outdoors. And so I switched over to geology, got a master's degree in geology, and then went on to my PhD work at Caltech.
Yeah. I guess that interest in the mountains is shared by many, and I guess many of us have really gone into our subject of interest, our lifetime subject of interest, because of a passion for the mountains. I think that's something that we both share, is it not?
I think so, and I think there's more to it than that, in that since the late 18th century and certainly into the 19th century, the great naturalists of the continent in Europe used to take their holidays in the Alps, and they would walk up a glacier and hit it with an ice axe or an alpenstock, and it would break as a brittle solid. Then they would get up on the peaks and look down and see what looked like flowing rivers of this brittle solid. That perplexed them. It was an enigma that had to be thought out, and that intellectual interest, I think, has spurred probably you and certainly me, also in terms of the study of glaciers.
Yes, it was in glacier dynamics, the structure and mode of flow of glaciers, that you became first interested in the subject, was it not?
Yes, right.
And can you tell us a bit about how your academic career went after your initial electrical engineering? Where did you go from there? How did it lead into the dynamics of glaciers and your studies on that?
Well, I think it was partly that interesting paradox of a brittle versus a viscous light liquid that is ice that got me rather stimulated into sort of an intellectual problem that had to be solved. I went in, got my master's degree from the University of Iowa in geology, but decided at that point, partly through mountain climbing, that I wanted to go and study under the best glaciologist in the country, and that was Bob Sharp at Caltech. So I went there, and I have never regretted that. I consider him my teacher, and he taught me a lot more than just about glaciers. For instance, he taught me that you have to question authority. I would come to him and make some statement, and he would say, well, how do you know? And I would say, I read it in this authoritative textbook. And he would say, how do you know? And that got me to challenge thinking and to try to make up my own mind about scientific problems based on observations and models that could be verified and so on. And I think that was the most important sort of general lesson that I learned in my graduate studies.
Well, you were looking at glaciers in your mountaineering, and you had your theoretical studies in university under Robert Sharp. Where did you do your first field measurements, and what sort of measurements did you do?
Okay, I did do a master's thesis on the glaciers of the Wind River Mountains of Wyoming, which is the largest mass of glaciers in the Rocky Mountains of the U.S. That was largely a study of where the glaciers are and how they grow and shrink.
Mm-hmm.
My PhD, on the other hand, was done in Canada on Saskatchewan Glacier.
Mm-hmm. Oh.
And you may have heard
Yes.
of that
I
glacier.
have indeed, because I've worked in the same area myself.
Yes, I know you have.
And indeed, I think we even find to this day little pieces of Mark Meier's equipment still coming down the
Yes,
glacier.
that's very embarrassing. I can only say that the debris left by the joint U.S. and Canadian services expeditions on the
that's right.
same glacier was even larger
Even
than mine.
larger, and there are other expeditions and so on which leave a lot of clutter on a lot of glaciers.
But what I tried to do there mainly was to try to get some knowledge on a basic question about the flow law of ice, and that is the flow law, we now call it the constitutive law of ice, different under pressure than it is, say, at the surface, where the pressure is only atmospheric.
Mm-hmm.
So I measured the rate of strain of the ice on the surface, which was a new thing to do, but relatively easy.
Mm-hmm.
And then I tried to measure the rate of strain as a function of depth by drilling holes in the glacier
Mm-hmm.
and encasing those in aluminum pipes and
Mm-hmm.
measuring the deformation of those things. It was partly successful.
Yeah, okay. And where did you go from there in your academic career? You were now at Caltech, and
I
you were
was at
working on the
Caltech.
Saskatchewan Glacier. and-
Yeah, and I had to support myself at Caltech, so I was part-time teaching at a nearby smaller university, Occidental College. While I was there, I was asked to and did organize a crevasse study expedition to the Greenland ice cap
Mhm.
to try to figure out how and why crevasses form, because it was at that time being recognized that this is a hazard. People can fall into them, vehicles can drive into them.
Yes, indeed.
And people wanted to know, can we predict where crevasses will be, and so on. So I spent some time doing that. And then I was lucky to get a Fulbright Award, which took me to Innsbruck, Austria,
Mhm.
where I came under the influence of the late, great glaciologist Friedel Hoenkes.
Yes. Yes, who in fact I met in around about 1970 or 71 when I was over there, and he in fact introduced me to Hintereisferner. Did you go up to
Oh, yes.
that
yes,
glacier
yes,
at that
yes.
time in the Ötztal?
Yes, a number of times.
That's one of those glaciers where there's been a very long-term monitoring program.
Mhm.
Now, I believe that later in your career, or soon after your Caltech experience, you began to be interested in the hydrology of glaciers. Can you tell us a little bit about how you got into that and what office you set up? I think it was in the USGS.
Yeah. While I was in Austria, we were there for an academic year, Luna Leopold, who was at that time the chief hydrologist for the U.S. Geological Survey, decided he wanted to restart a program in glaciology as part of the Water Resources Division of the USGS. And so he approached me and asked if I could head up that effort, and I said, that sounds great, I'll do it. I created the so-called Project Office Glaciology
Mhm.
in Tacoma, Washington,
Mhm.
a location which put me in quite reasonable proximity to glaciers. And I began a little program there, hiring a number of people, building up stations and so on.
People who have been in the business of glaciology since that time, the late 50s, I guess
Oh,
that
yes.
was, and through the 1960s, and
Yes.
right up, some of them right up to the present day. This was a sort of school of glaciology, if you like, that you were beginning to set up, just I suppose as Robert Sharp had set up a school of glaciology. So now you were beginning to set up your own, not exactly an academic teaching school at that time, but it was a place for training and developing techniques and programs. Now, what programs and on which glaciers did you begin to work at that time? Late 50s, early 60s?
The first one we set up was at South Cascade Glacier which is in, of course, the North Cascades of Washington. The,
Ironic.
the head of the South Fork of Cascade River. And we put up a nice little research station there, a nice enclosed stream gauging station, a second very good stream gauging station on a non-glacial stream, and started a program in glacial hydrology, glacier meteorology, glacier mass balances, and glacier dynamics. And in fact, as you say, it was a bit of a teaching place because it was a spot where now a lot of data were being collected, and so that other investigators could come in and rely on this infrastructure or background of data to build their own projects. So we had chemists doing chemical weathering, and we had meteorologists studying drainage winds, and we had dynamicists studying glacier dynamics and so on. It was, and still is, a
Yes,
very
that's
useful
right.
setup.
Now let me just get this straight, because on the Saskatchewan Glacier, early on, this was not part of a long-term monitoring program. This was just, if you like, a one-off
Yes, right.
research project. And that's rather different from what you're now talking about on South Cascade Glacier, where a long-term monitoring was set up, hydrology, energy balance, mass balance of the glacier, but that monitoring program allowed other research projects to take place within
Yes,
a
exactly.
long-term program. Would you think that's one of the main benefits of long-term monitoring, quite apart from the necessity of tracking weather and climate and hydrology through time?
Oh, I think so, and we set that up with the idea of making it a long-term program as the major objective. In fact, there's a difference in what a government agency can do and what an academic institution, a university, can do. At Caltech or any other university, such as University of Colorado, our projects are usually short-term. They're based on an individual PhD dissertation or something like that, or a series of grants from some particular funding agency. They come and go in a matter of years. Whereas a government agency can usually guarantee some longevity to the programs, and this opens up the very important point that you can get long-term records that you can relate to changes in climate and so on. And so we set it up with that in mind.
Yes. Now that really was one of the precursors. There were also other glaciers in Europe which had been studied for a long time in Sweden, Norway, and Austria, Switzerland. But that really was the precursor of what in the 1960s turned out to be, under your leadership, among others, the International Hydrological Decade. Could you give us a little bit of background on how that started, and perhaps talk a bit about what that program was all about?
Surely. I was somewhat involved in the International Geophysical Year. I was quite young at the time, but I was involved peripherally in this, and I began to recognize the great value to having a long-term interdisciplinary approach to many of the earth sciences. After the IGY people began to realize that, gee, we ought to start a program like that in hydrology, but obviously we can't solve water problems of any import with just 1 year of study, so let's call it a decade. The International Hydrological Decade was formed, and UNESCO committed itself to supporting this. And now, having a mechanism set up, we in the glaciological community jumped in with both feet and said, oh ho, here's a chance to put international programs together that will solve some of our big questions on a more international and long-term basis. And so by that time, the International Commission of Snow and Ice, at the beginning of the IHD, it was led by Friedel Hoenkes. I mean, IHD was led by Friedel Hoenkes, and I was one of the vice presidents. And then 4 years later, we just changed roles, and I was in charge, and Friedel was the vice president, along with others from Russia and Sweden and Switzerland and so on. We decided to promote programs on glacier variations, on glacier inventories, and the one that I was particularly involved in had to do with the ice, water, and energy balances at glacier stations.
That's how much comes in and how much goes out on
Exactly,
an annual basis.
yes.
And, yeah.
What is responsible for this turnover of mass on a day-to-day, month-to-month, seasonal, year, decadal, etc. basis?
Mhm.
And so we tried to set up a number of stations around the world, especially on some grand transects, which didn't all materialize, but still a number of other stations like the South Cascade Glacier were set up in Canada.
Yes.
Canada had a very nice program
Yes.
with the IHD, and I'm
Yes.
sure that you were involved in
Yes.
getting that started, and I know you were highly involved in running probably the preeminent glacier station as part of that program on the Peyto Glacier.
One of the longest, and that was set up by our colleague and friend Gunnar Öström from Norway.
From Norway.
And that was an interesting example of international cooperation. Gunnar Öström had been a glaciologist in Norway for many years, and having had experience on Norwegian glaciers, he was asked to come across to Canada and set up our glacier program, or part of our glacier program in the Rockies and in the Coast Range and in the high Arctic. But the IHD, the International Hydrological Decade, wasn't just limited to Europe and North America, was it? It was really trying to get a handle on global conditions, and perhaps you might just expand a little bit on the extent of the network, or the hoped-for network, and whether in fact it came into being.
We had hoped originally that there would be one north-south transect from Arctic Alaska down the west coast of the Americas through southern Mexico and into South America and all the way down to Tierra del Fuego and the Antarctic Peninsula. A second transect was along the Arctic, an east-west one, and a third one was at about between 40 and 50 degrees north latitude.
Mm-hmm.
Not all of these transects were filled out very well. For instance, we could not get any of the Latin American countries to put up enough of resources to have a long-term glacier monitoring program on their glaciers. We did have other glaciers, though, that came into the program, even though they were not on transects, such as one in New Zealand, one in Indonesia. And of course, we had many stations set up by the Russians and later the Chinese. So the east-west transect below the Arctic Circle, the one at temperate latitudes, was very successful.
Very successful, and indeed it was and has been quite successful in Central Asia, as you pointed out, in the Tian Shan Mountains, in the former Soviet Union and China, and down into the Pamir Mountains. There have been some long-term and very valuable glacier monitoring in those regions. But I guess there are other parts of the world which, in the Himalaya especially, the Karakoram, which were largely untouched in that by that IHD, or were they? Were the programs set up there?
Well, one of the purposes of the IHD, and it became even more important with the follow-on programs of the International Hydrological Program, which was sort of open-ended and still exists, was to make sure that the benefits of science as developed largely in the industrialized nations were going to be benefiting people in all countries, including the developing countries. And so one of the things that ICSI did was to try to bring scientists who had earned their scientific credibility on intensive programs in Canada, for instance, or Switzerland or whatever, to some of these other parts of the world to assist in developing their programs for the benefit of their water resources problems and so on. And we all know that you, Gordon Young, were very instrumental in doing this in the Himalayas and in, I think, the Andes also?
Not so much the Andes, but the Karakoram in particular. That's where I, in the 1980s, along with many colleagues from several universities, funded primarily from Canada, had a very, I think, successful program. Not really long term, but for 4 or 5 years anyway. I might just comment on the Andes that I was recently in Bolivia, and lo and behold, lots of things are happening in the tropical Andes now, in Ecuador and Peru and Bolivia, as well as further south out of the tropics in Chile and Argentina. There are several stations coming into existence. They have come into existence over particularly the last decade, much later than the original International Hydrological Decade 1965 to 74, but really inspired by that decade and by the subsequent International Hydrological Program. So although the programs that you mentioned didn't come into being simultaneously everywhere, they in fact have they come into being later in time, which is an interesting
It may just take time to, first of all, to develop support within countries, secondly, to get the people. And I think it's in part a matter of people studying abroad or rubbing shoulders at meetings with people abroad and beginning to realize as individual scientists who work in the trenches that, you know, maybe we could get something started in our own country. And
Yes.
It's taken a while, but it's gratifying to see
It has
that
taken a while.
things are happening.
Yeah, I think you were really quite fortunate or lucky in a way to have been in at the beginning and have been instrumental in pushing that big thrust for the International Hydrological Decade. I came in a little bit later and was in fact a beneficiary of it because I, like many students at my time in the mid-60s, mid-70s, learnt from our experiences on the glaciers which you had and your colleagues had sort of laid out, and learnt from the programs which you had laid out. And I guess this is part of the passing on of experience and learning.
Well, that's nice to hear, but that was our intention.
Yes, well, it's I think it's worked, and in that sense. But perhaps we could come back, instead of just talking about programs, the IHD and the IHP, we could come back to some of the science, the research that you had been interested in through the 50s and 60s. You were talking about glacier dynamics to start off with, and strain rates, glacier motion, crevasses, and so on. How did your own scientific investigations develop after that initial interest?
Well, partly because I was a member of the Water Resources Division of the USGS. I decided it was time to get interested in problems of glacier hydrology, including the distinctive characteristics of glacier runoff. And we defined, for instance, the natural regulation of glaciers, in which in a very dry year they produce more than normal runoff, and in a very wet year they produce less than normal runoff. And this is a counterbalancing effect that stabilizes stream flow from year to year in mountainous areas that have glaciers. We also got interested in such things as glacier outburst floods and a number of aspects of glacier meteorology, which were not too well known. And I also got into the major problem of how do you measure the mass balance of a glacier, the mass input minus the mass output, in a verifiable and satisfactory way.
Yeah, what sort of techniques did you set up then? What sort of methodologies for the measurement of mass balance, the input of snow and water from rain, the melt of ice and snow? How do you do it?
Well, we did all kinds of things. What I realized was the fact that although many people in many nations had been sticking stakes in glaciers and digging snow pits and measuring the snow thickness and the snow density, and then adding this all up, integrating it over the area of the glacier and pronouncing that the mass balance is such and such, minus 2 meters of water equivalent or plus 1 or whatever. And I wondered sometimes, were there not some errors in this measurement that would bias the results? So I started to try, at least at South Cascade Glacier, to check the mass balance measurements by 2 other methods. One was a geodetic method, which is straightforward, in which you simply measure the volume change of the glacier over time. And the third one was a lot of fun, but very difficult, and that's a hydrologic method in which one measures the precipitation input as snow and as rain, and the meltwater output, which is both rain and snow and ice melt, and constructs a hydrologic water balance, you might say, of the glaciers.
But you didn't mention one or two other things which I believe complicate the situation, the evaporation. Is there much evaporation? This, I think, has always been a question.
Well, of course, we had to measure that in terms of understanding the mass balance, and especially in regard to this water balance kind of problem. But let me just mention that water balance one. We tried a brute force attack on it, which meant we had little precip gauges all over the basin, many, which we measured on almost a daily basis. We had a time-lapse camera measuring every day the movement of the snow line, the area between where more snow accumulates and is lost, in the area where more is lost than accumulates. That was measured every day. Of course, we had superb stream flow measuring stations and all the other things. We had evaporation lysimeters buried in the snow and the ice and so on. And we actually constructed daily water balances. We didn't necessarily believe the daily values, but when we accumulated them over a week or month or so, we thought they were quite believable. And one of the very interesting aspects of that was, still to this day, a bit of an enigma, although other people now have seen the same thing, and that is that if you measure the amount of water mass going into the glacier during, say, a 6-month summer season, and you also measure the amount coming out, and you measure the change in volume of the glacier itself, the equation does not balance because liquid water is being stored in some mysterious place down within the glacier and then released. And we were able to measure and calculate that for the first time, which is quite interesting.
It's quite something, yes.
Yeah.
And I suppose sometimes water escapes into the ground and into the rocks beneath, and there's a groundwater
That can
loss
happen.
or indeed
Yes, yes.
addition in some cases.
That can
Was that the
happen.
case in South Cascade?
We picked South Cascade Glacier for a number of reasons, one of which was that it sits on a very hard granitic pluton with very little porosity, so it's very unlikely that much water would infiltrate.
So that particular glacier sits on rocks which are conducive to studying the hydrology.
Yes.
There are many glaciers which sit on porous rocks.
Right.
And this brings up the whole idea of whether the glaciers that you picked for study are representative of others. And maybe you could talk a little bit about this problem of choosing glaciers. How did you choose that particular glacier or your group of glaciers? What criteria did you use? And indeed, are they representative in some way of the whole suite of glaciers in a basin or in a geographic area?
That is a loaded question.
Of course it is.
I think I've been wrestling with the question of what is a representative glacier, unquote, just like what is a representative drainage basin,
Yes.
unquote,
Yeah.
for my whole career. And it's very, very difficult to answer that question. I could use the word typical, but I'm not so sure that representative has a meaning that I can at least understand.
But of course, in the literature, it has been used a lot, and perhaps
Yes, of course.
that's misleading in
I
just
think
the
so.
ways that
There
you're
are
talking about.
IAHS symposia that have been held on representative and experimental basins. But I do not understand, frankly, what is meant by the term representative. I would say that the glacier we picked is typical of those in the North Cascades. It lies on the common kind of bedrock. We picked it especially because of a good stream gauging site, an enclosed basin which we could define very precisely, a surface that we could get around on, which maybe makes it a little untypical
Yes.
in some regards.
Yeah.
There are steeper, more crevassed ones that we could have picked, but would have had a hard time working on.
Was it typical, the South Cascade, was it typical in size? compared to the others? About the same
Yeah,
size?
about, well, in the size spectrum, it's
Yeah.
sort of in the middle.
Uh-huh. The Pato Glacier, on which I've worked for some time, which was one of the IHD glaciers, is quite a lot larger than many of the little glacierets in the larger basin in which it lies. And one of the challenges that we have now is to extrapolate what we've learnt from our studies on the Pato Glacier to the glaciers roundabout, in order not just to understand the hydrology of a relatively small basin with a lot of ice in it, but to look at the contribution of melting ice in a relatively large basin which has a number of different sized glaciers in it. This is I think a perennial problem.
Well, the problem, as you mentioned it, is a problem that I happen to be wrestling with right now, if we want to get into that at this stage. It's a scaling problem in some respects.
Yeah.
And I've been highly involved in trying to understand the contribution of the small glaciers of the world to global sea level rise. By small, I mean all the glaciers of the world except for two, the Antarctic and the Greenland ice sheets.
Which account for, what, 95% or something of the
volume, yes, of course.
the volume of ice?
But their contribution to sea level is small compared to the contribution of these other glaciers like the Pato and many of the others. And my problem is that we have good measurements on a few glaciers, almost all of which are the size of South Cascade or Pato or Hintereisferner or the Storglaciären, which has the longest mass balance record, that's in Sweden.
Yes.
They're all about the same size. They're almost all in temperate mountains.
And how big would these glaciers be, roughly? You say they're all about the same size, but...
Well, I'm saying the ones that have been well studied. They're
20
the
square
order,
kilometers?
well, from less than 1 square kilometer to 20 to maybe 50, some of the biggest. They're all in that range of, 10 square kilometers, that order of magnitude.
And most of our measurements of mass balance have been made on glaciers of that sort of size.
Yes. And yet, when you look at the glaciers of the world, they range in size from some undefined lower limit, less than 1/10 of a square kilometer, on up to glaciers such as the Bering or the Malaspina Glacier in Alaska, each of which has more ice than all of Europe, on up to much larger ice caps in Arctic Canada, the Antarctic Peninsula, and so on. And so the spectrum of glacier sizes ranges over many, many orders of magnitude. And we somehow have to extend our measurements of mass balances and the dynamics, which are important, the response times, over this suite of many, many orders of magnitude in size. And that is a very difficult problem that I'm wrestling with now.
Yes, and it's a problem which has great significance for subjects like sea level change, which you've been investigating so much. And I believe that one of part of your studies show that the Alaskan glaciers, those large glaciers, very dynamic, very fast throughput and big volume of throughput of ice, it's changes in the dimensions of those particular glaciers which have a disproportional effect compared to their size on sea level rise.
Yes, a study I did it was published in 1984, suggested that 40% of all of the contribution to sea level rise of the small glaciers of the world comes from those around the Gulf of Alaska. And a large percentage comes from the Patagonian ice sheets, ice caps, and third in size and in contribution are the glaciers of Central Asia. But the glaciers, the large Piedmont glaciers of Alaska and the Patagonian ice caps are glaciologically almost unknown. We have very, very little data, even though they're so important.
Yes, that's right. It's good to see that in Patagonia now, Argentina and Chile and Japan and others are making some good efforts to,
Right.
and some interesting studies being
It's
done.
just
in that
getting
area.
started,
Just
yes.
getting started. It's amazing that such a large ice mass would almost just be getting started in the very recent past to look at
Yes.
glaciological characteristics. One of the areas that I have looked at is in the Karakoram in northern Pakistan, and I found that very interesting and challenging because those glaciers, some of those big valley glaciers, are sort of intermediate between the Alaskan Piedmont glaciers that you talked about and the very small glaciers which we started talking about. Some of the glaciers in the Karakoram are hundreds of square kilometers,
Yes.
not thousands, but hundreds of square kilometers in size. And we've been measuring some of the thicknesses. Some of them are more than a kilometer thick in places. So there are large volumes of ice involved. And one of the things that, one of the challenges that we've found there is that because of the great altitude, we could not go up into the accumulation areas and measure as we would in the Rocky Mountains or in South Cascade Glacier. And because of the huge volumes of meltwater coming from the streams, it's very, very difficult to get a handle on the hydrology. So we had to develop different methodologies for looking at the glaciers. And one of the things that we did, and I think it's been done on the Athabasca close to by Stan Patterson some time ago, next to the Saskatchewan on the Columbia ice fields, is to try to calculate the flux of ice through a cross-section. And I don't know whether you've had an experience of measuring the thickness of glaciers and the rates of flow at the surface and trying to infer the flux through a cross-section. But if one can do that, it does give, in very simple terms anyway, an estimate of how much water is being lost below that particular ice section on an annual basis. Have you had any experience in that
No.
sort of?
Lots.
Yeah. Perhaps this might lead into you talking about your projects on the Columbia Glacier.
Yes,
which is a sort of a natural lead-in from this topic we've been discussing.
Well, what you just mentioned, Gordon, is a very powerful tool. And in fact, if you can define a cross-section, measure the thickness, which can be done with radar methods now quite easily, and measure the flow at the surface, you can also probably calculate the flow at depth, at least approximately. And then if you also measure the rate of change of thickness, is the glacier getting thicker or thinner at that cross-section? If you know that, you can calculate the so-called balance flux caused by the accumulation above that point or the loss below that point or whatever. You can also calculate the thickening or thinning fluxes, and knowing the two, you know a lot about the glacier. Now, we studied for another completely different reason a big glacier in Canada, I'm sorry, in Alaska, that has an area of just over 1,000 square kilometers, the Columbia Glacier.
And the Columbia Glacier that you studied is not to be confused with the Columbia ice field in Canada, is it?
That's right. And it's also not the Columbia Glacier in the North Cascades of Washington either.
Okay, just
Anyway.
yeah.
Anyway, the Columbia Glacier, which we studied for another reason, we did need to know, we had to model the future behavior of that glacier. So we had to have a dynamic model of its flow, which meant we needed to know these parameters throughout the whole glacier. And we did something that I think has never been done before, and that is we made many surface measurements of the mass balance, the accumulation or the ablation. We made measurements by repeated aerial photography of the rate of thickening and thinning of the surface. We made measurements by stakes and also by repetitive aerial photography of the velocities and strain rates. And we essentially solved the flux equation at every grid point. We looked at the flow divergence of the glacier as a function of its spatial extent at grid points. And the
Grid
interesting
points, how far apart?
Oh, I think it was some funny number of meters, 500 meters, something like
Half
that.
a kilometer or so.
Yeah, something like that. And we we also took all of these measurements and put them into some massive computer program so that we knew that this glacier was obeying the equation of continuity. Now, there's only one equation in all of glaciology that I have complete faith in, and that's the equation of continuity. And so we adjusted the data within the range of its probable error for each grid point to obtain this consistent analysis of thickness, velocity, surface input, thickness change, and so on. And so it's a very unique data set.
It is, yes. It's recognized.
It's been used by
as such.
other people for
Yes.
other purposes since. And it's
That's right. It's really valuable to have a very complete and thorough and accurate data set, something which we might come on to in a moment. But the particular reason why you chose the Columbia Glacier was, I believe, because it's a floating glacier at its tongue. Is it? It wasn't that?
No. But yes, we could. It's a very interesting glacier. And let me back up a little bit. I had with me in my group in Tacoma a very, very interesting person named Austin Post.
Yes. Yeah.
And I just have to say a little bit about Austin Post. Some people essentially are self-educated. They have an enormous power to observe something and to sort of, in that observation, to say, okay, this makes sense and that makes sense, but there's something wrong here. I've got to figure out why that's happening. And he has this acute ability. Austin Post never did get a PhD. He never did go to graduate school. He never did go to college. He didn't even finish high school. In fact, to hire him in the U.S. Geological Survey, the authorities said, we can overlook all of these things, but we can't overlook the fact that he didn't go to high school, or didn't finish high school.
Didn't finish high school.
So I had to send to his high school reprints of articles he'd written that were published in the most competitive, prestigious journals, Science Magazine, Journal of Geophysical Research, and so on. I sent them a stack of reprints, and they sent him back a high school diploma.
Should have sent him back a couple of PhDs, probably.
But he's an internationally accepted scientist based on his own power of observation and reasoning. One of the things that he did was to really define glacier surges. I won't get into that now. The other thing that he noticed while doing airborne reconnaissance studies of glaciers of Alaska was that the glaciers that ended on land seemed to be advancing and retreating in a way that seemed intuitively reasonable. But the glaciers that ended in the ocean by breaking off of icebergs, calving we say, seemed to be behaving in rather anomalous and asynchronous ways. And he was trying to figure out what caused that. And so he looked at the charts and so on, and he found out that the glaciers that end in the sea, that end in shallow water, are essentially stable, or maybe advancing a little bit, not retreating. The ones that end in deep water are retreating very rapidly. And he looked all around Alaska, 50-some glaciers, and he found that this held true with every glacier except one, and that was the Columbia Glacier. It had been stable since it was first mapped by George Vancouver in 1792, yet the nautical chart said deep water right in front of it. So in 1974, we organized a little expedition and went in and measured the water right in front of the glacier and found, in fact, it was shallow, so Austin Post could breathe a sigh of relief, you know. His theory was not negated. But we also noticed something else, and that is that the glacier appeared to be thinning. Large embayments were forming in the front, and it looked like it was rather precariously stable, and that it might retreat from a moraine shoal that we had found. And there might have been deeper water upstream from that shoal, which would have caused rapid retreat, which means the rapid breakoff of icebergs, which then flow out into Prince William Sound, Alaska, flow across Valdez Arm,
Mm-hmm.
And of course, at this time, the Trans-Alaska Pipeline was being constructed, and soon there would be tanker traffic in Valdez Arm, and therefore we told the powers that be, the Coast Guard and so on, about this. They said, go study it and give us a prediction, and they only gave us less than 3 years to do this and tell us what's going to happen to Columbia Glacier in the next decade or so. So we took the money, did the study, developed all kinds of new techniques like radio echo sounding of glaciers, measured its dynamics, modeled its dynamics. We developed, by studying all the major iceberg calving glaciers of Alaska, we developed relations that we could use to predict the amount of calving, the calving speed as a function of water depth. We put that all together as a predictive model and came back and said in June of 1980, said, here is our prediction. It's going to retreat in the next few years, and the retreat will be very rapid, and there will be a lot of icebergs discharged. And of course, as soon as we did this, the glacier just sat there for a year or two.
That's what glaciers do.
But then it went into this rapid retreat, so we breathed a sigh of relief at that point.
And it did calve at the rate of, what was it, so many thousands of cubic kilometers a year, was it?
No, not thousands of cubic kilometers, but it's quite a few. I forget the number right now, but it's huge. It's measured in many cubic kilometers per year. I once figured out how much ice it was per second and found out that you could ice an awful lot of drinks of the amount discharged from that glacier per second.
Right. That's an interesting example from the Coast Guard point of view of a human need driving and helping
Yes.
a scientific study.
Right.
And I guess we could probably quote quite a large number of those around the world, especially perhaps now in the water resources area, in those dry areas near to mountains, dependent on mountain water, where the need to know how much water there's going to be for supplying water supply, how much there's going to be in the future, and how glacier melting and how glacier shrinkage is going to affect the long-term supply of water. And in fact, that's one of the things that I'm particularly interested in the Rocky Mountains of Alberta now, because southern Alberta is dry country, less than 300 millimeters of rain per year in many parts, and sitting right next to that dry area is the source of the rivers. High mountains, snowpacks, glaciers, but glaciers which are getting smaller. So the question that I'm interested in now is what is the contribution of ice coming out of storage into the rivers?
Before I answer that, can I just back up one moment and say a direct outgrowth of the Columbia Glacier experiment, which was really motivated by trafficability of tankers. Now, the Coast Guard is supporting a study that's being funded by the Department of Energy that wants to get better information on sea level rise in the future due to global warming. And the question they've put to us, asked us to study, is with global warming, is the rate of iceberg calving from the Greenland ice sheet going to increase or not? Because this directly involves how much ice is being drawn down off the land and put into the ocean. And so we're applying the same sort of Columbia Glacier theory in observations and modeling now to the larger glaciers that drain the Greenland ice sheet.
Those are outlet valley glaciers, are they?
Yes. Bigger, not necessarily faster, but big. And so that work is now being applied to the sea level prediction problem, which has some societal interest. But you mentioned the water supply problem. This is particularly acute, I think, for some developing countries in the Andes and the Himalayas, Central Asia especially. In that we know that the glaciers of the world are shrinking in general. The mass balances have been negative since the turn of the century in general. Many of them are disappearing. What this means is that while they are thinning, the amount of water, a certain amount of water is coming out of storage, it's feeding the rivers, it's being used by humans for irrigation and domestic supply and hydroelectric power and all those things.
Mm-hmm.
But as the glaciers disappear, this extra source of water will dry up.
Yes, almost inevitably, I suppose.
Yes.
It will eventually dry
It will
up.
eventually dry up,
Mhm.
and it will certainly is diminishing now to some extent. And so that extra source of runoff is
Mhm.
a cause of concern.
Yes, that's right. So in the long term, there's a sense of fear that the water supply might, total water supply per year might diminish. One of the things that we're looking at is the effects on seasonal water supply, because at least in the Rocky Mountains and away from the equatorial regions, the glaciers melt much more. The ice melts much more rapidly in late summer, and that is precisely the time when the farmers need more water for irrigation, as evaporation rates are higher. So precisely at the time of greatest demand and less supply from other sources, so the glaciers kick in. And in fact, this brings us back to a point that you made earlier, that in summers with little snow or years with little snow, the glaciers actually give more at the critical late summer time.
Yes, exactly.
Yeah.
Yes, yes.
And from year to year there are differences, so that the glaciers give water in those critical years of great stress, high demand, great stress, when other sources of water, snowmelt in particular, are lower.
Mm-hmm.
So the glaciers acting as a safety valve in times of great
Yeah.
stress their effect might be lessened in the future.
The other side of that coin is the fact that hydrologists in general have developed, quote, rainfall runoff models
Mm.
that are applied all around the world to predicting runoff.
Mm.
And unfortunately, if there is a glacier in the drainage basin, then it gets absolutely the wrong result. And so we do need better models incorporating the unique aspects of glacier runoff.
Mhm, mhm. Another aspect of glacier runoff, quite apart from overall water supply, that you mentioned just a few minutes ago, was floods from glaciers. And perhaps we might just talk for a few moments on the ways in which floods are derived from glaciers and glaciarized areas, and perhaps think a little about the importance of understanding glacier dynamics and glacier flow as they impact on the creation of lakes and the sudden release of waters.
Yeah, I've personally been involved only peripherally in this subject,
Mhm.
although I have published some simple little analyses. The point is that a glacier can flow down a valley, blocking a tributary valley,
Mhm.
or it can flow out of a tributary, blocking the main valley, or it can just sit on a volcanic hotspot. And in all of these cases, a water body is created, either under the glacier or behind the glacier or something like that. And then you have an interesting situation. Somebody said the media is the message. The liquid water is being dammed by its own solid.
Mhm.
And what this means is that if you get a little trickle started, tiniest little trickle between grains, that dissipates heat, that moving water dissipates heat, or it brings water slightly above freezing temperature in. That enlarges this little tiny conduit, allowing more water to flow, allowing more enlargement, allowing still more water to flow. The net result is that once this gets started, then it builds up almost perfectly in an exponential arrangement or relation
Mhm.
until all of that water is drained in a massive flood.
Mhm.
It can be a small pip on a stream flow measurement, or it can flood a whole alluvial fan or a village or
Yeah.
whatever. It can be
Yeah.
devastating. It can whip up rocks and create mud flows and
Mhm.
so on.
Mhm. There have been lots of examples of those
Oh, yes.
around the world. One very classic example from the Karakoram Mountains in what is now Pakistan and India, occurred in the late 1920s, when a large glacier blocked a valley, a lake was formed, and then the lake suddenly released. And it took several days, 4 days I think, for the flood crest to move the 1,400 kilometers down to where there is now a large dam. There wasn't at that time. And 1,400 kilometers below that outburst point, the water rose 18 meters, 50 odd feet, which is quite remarkable. And in fact, in 1841 on the same river, a whole army was drowned on the floodplain, resulting from that.
Yeah.
And I think that the magnitude of some of these catastrophes is seldom realized. You mentioned volcanoes, a glacier sitting on a volcano.
There are two examples of that. One I just should mention is the Icelandic experience, in which a particular ice cap sits over a volcanic hotspot, which causes the ponding of water under the glacier, which then releases in a Jökulhlaup outburst flood. And those floods have been estimated as having a discharge larger than the Mississippi River at Vicksburg.
Yeah, it's quite amazing.
Yeah. But to get into volcanoes, yeah, that's a very interesting situation. I used to live in Tacoma, Washington, which is named for Mount Tacoma, but the English, of course, named it Mount Rainier after some obscure English naval officer. Anyway, Mount Tacoma, or Rainier, has experienced a lot of mud flows and floods coming down its glacial valleys. And usually these have been ascribed to rainfall events, and rainfall is not uncommon there, so this is quite possible. But I started studying this situation and found there's very good ways to prove that, in fact, the water is being stored under the glacier, which is amazing because these glaciers are on a steep volcano. And you wonder, how can water be stored under these steep, thin, highly crevassed glaciers out of sight? Then they suddenly break through the ice and come down and cause flooding. We had a very interesting case of that in 1967, in which on our Labor Day weekend, which is a big camping and tourist time, one of the campgrounds below Tahoma Glacier was closed because of forest fire danger. The next day, that whole campground was buried under more than a meter of debris. And so, how many lives were solved by that one? Lives were saved, I'm sorry.
Yeah, saved by that knowledge. It just goes to show that understanding the internal hydrology of the glacier is extremely important and useful, not just from knowing how the glacier moves, but in this very practical way, human impact way, and impact on geomorphological processes below the glacier. They're all related to what happens on and underneath and inside the glacier.
My first real prediction that I was asked to make was a case like this. In Alaska, there is a very large glacier called the Knik Glacier, and it feeds the Knik River Valley, and it used to dam up a major lake called Lake George. Now, downstream from Lake George is the Alaska Railroad connection between Anchorage and the largest city in Alaska and the interior. Also the highway connection between Anchorage and the interior. And Lake George used to burst out every year or every few years in a big flood that would wipe out bridges and these transportation arteries. And shortly after I was hired by the Geological Survey, the Department of the Interior that runs the railroad and so on said, hey, now that the USGS has got a glaciologist, we need to have him come up and look at the Lake George situation. And so I said, well, what's the point of my going up there? I can wave my arms at it, but there's nothing you can do about it. And they said, well, come up anyway. So I went up anyway and studied it, and and looked at air photography and so on over the years and made some little calculations on the discharge and wrote a little report in which I said that the situation's going to go away in a couple of years. And it did. The glacier was thinning to the point where it wasn't going to be a problem, and it hasn't recurred since.
These problems for humans nearby and sometimes quite far away from glaciers, but related to what happens in the glaciers, is very interesting. And one glacier that we were concerned with some time ago was the Berendon Glacier, which is right up near to Alaska in Canada. In fact, almost on the border. And there are a number of very interesting glaciological features or questions which impact on human beings, in particular mining. There were enormous avalanche dangers for the roads, as it was a very steep terrain and a great deal of snowfalls in winter, 10 meters or so in winter. There was a glacier discharge of a glacier lake problem, tide lake ponded back by the Salmon Glacier, and occasionally that would discharge and it would wipe out the road.
Yes.
And then the mine itself, a copper mine, had adits, tunnels drilled into the rock, and they wanted to go under the glaciers. And so they had to know how deep the glaciers were. So here were several glacier-related problems for just one particular mining activity. And I think it's a very interesting example of needing to know how nature works, glaciological nature works, as impacting on human activities.
There's problems similar to the Berendon have been encountered in Norway and the Alps and many parts of the world.
In Latin America, there have been these cases in the Andes of glaciers. I think the mountain in Colombia, El Ruiz, where there's essentially an ice cap or a number of little glacierettes sitting atop a volcano, and when heat is injected, perhaps sporadically, into the ice, then this can create sudden floods and mud flows. And in that case, just a few years ago, I think it was 22,000 people were killed in the valley below. What happens in the mountains is very much related to human activity. And other examples that have been studied recently in the Himalaya relate to a totally different set of processes, where lakes at the snout of valley glaciers ponded back by moraines, moraine-dammed lakes, can suddenly overtop the moraines and suddenly create a flood. Or if a landslide occurs into the lake, the entire volume of water can be slushed out in one big slop, if you like, and it goes down the valley very suddenly with real catastrophic events. So these are all examples of there's needing to know what happens.
There's a lot of societal justification for studies from the point of view of natural hazards, and there are many that are caused by glaciers.
Can we now get on to going back to your career? And we sort of left it in the hydrological decade and perhaps a few years after that. But I believe you more recently got interested in remote sensing methods on snow covers.
Yes, I did for a while.
Could you go a little bit into that? Because here's a different technology, different methodology, perhaps.
This wasn't exactly more recently. It was really back at about the same time. I began to realize that we needed something more than just air photography to understand snow cover. And at that time, NASA was just beginning to put together a program on Earth observations. And they decided we ought to have some test areas for different kinds of Earth observations, such as vegetation, soil moisture, and with a little prompting, they decided we needed one on snow and ice. So I said, I've got just the area you need, South Cascade Glacier. So we, in concert with NASA, investigated the feasibility of of many kinds of remote sensing devices and measuring snow and glaciers. One of the things we did was to develop a very simple method of using, based on gridded maps, of using high-resolution visual images, like from what we now call Landsat, and classifying these and determining whether there was snow or was not snow in each grid box. This becomes very difficult in the mountains, partly because of forest cover, and partly because in steep mountains, some of the area is facing right into the sun and is very bright, and some of the areas are in very deep shadow, so the reflectance, the radiance, varies from nothing to more than saturation. And we developed multispectral techniques to make that classification and simple little algorithms to put the data together, especially for snow-covered regular drainage basins, to watch the change in snow-covered area, especially in the forested regions of the Northwest. But I also got very interested in passive microwave radiation for the simple reason that passive microwave works day or night through clouds or clear sky. And furthermore, it can be measured in many different wavelengths, look angles, and a couple of polarizations. Because of this, you have a lot of tools to use, a lot of different variables that you can put together to understand the snow cover. And we made some real progress for a while. We had some experiments in which we contracted with a firm to put microwave radiometers on the ends of big cherry pickers so they could look down at the snow. We did such absurd things as we wanted to measure cold snow, but the weather turned warm.
It always does when you want to measure.
Yes, so what we were doing, and I'm glad nobody was there watching and wondering what we were doing and then writing it up in the newspapers, but we knew that the snow got cold at night, and so at 2 o'clock and 3 o'clock in the morning, we were running all over this huge area, collecting that little bit of cold, frozen crust, bringing it back to our test area, disaggregating it, and making a cold snowpack, which we could then measure.
The things you do for science, Mark, it's amazing.
If anybody had seen this, whole bunch of us were running around collecting this snow crust. Anyway, we found out that in fact passive microwave radiation has great potential for measuring the existence of snow and whether it's wet or dry. In some aspects, I've left the area because I didn't understand why we were getting these responses. I told the theoreticians, tell me, what is it about the volume scattering in a porous medium that gives us this interesting and peculiar response? And they tried different approximations to nature and never came up with a good explanation. So since I didn't understand it, I decided I'll wait until they figured it out. Then I'll go back into the, you might say, the field observation mode.
Yes.
Well, I've never gotten back to it.
But you'd probably agree with me that remote sensing over the past 20 to 30 years has gone ahead by leaps and bounds.
Absolutely.
And although there are still many problems to be solved in interpretation and so on, in the snow and ice field, as well as in many other fields, earth sciences have benefited very, very greatly by this change in technology.
Absolutely.
And I guess change in technology over the last 20, 30 years in many areas has been remarkable and has allowed us to do things now that we couldn't possibly have done 10, 20, 30, 50 years ago. And I suppose we're lucky to be living in an age when things are technologically changing. I don't know whether they're going to continue to change at that rate way on into the future, but we're certainly living in an interesting, or have been living in an interesting era from that perspective.
Oh, absolutely. And I'm very excited about the present day international global change arena. As you say, we have new tools. We not only have remote sensing that can give us a synoptic, spatial view of nature and many, many different variables of the Earth. We also now have computer power that makes very sophisticated models possible. We have a new program of international cooperation called the International Geosphere Biosphere Program, which has spawned a number of other sub-programs, all of which I think are bringing nations together
Yes.
in some of these more global issues. And finally, we're getting some realization, at least, of the importance of interdisciplinary research.
Yeah.
So all of this is coming together, I think, in a very exciting new era.
It is. Now, well, let's take up this theme then of international activities and international organizations. And again, perhaps we could begin with, from your personal viewpoint of how and why and when you have become involved in international activities. You mentioned the IHD, the International Hydrological Decade, but there were others, I think, before that you were involved
after
with.
that.
And of course after that, and of course since. Can you talk a little bit about your involvement in these activities?
The one that I'm most proud of stemmed from the fact that I forget exactly when it was, about 1979 or 80, something like that. A number of wise people, I'm afraid it's wise men, sat down and said, you know, the International Geophysical Year was so successful, it's now been 25 years or more. We need a new international thrust. Let's put our heads together and devise a new international program broadly based on the Earth system, and let's bring biology into it, which was not in the International Geophysical Year. Well, there was a symposium in Canada, and some people in our National Academy of Sciences got together and sort of sketched out a plan and distributed it. And I was, in fact, at the time involved in our U.S. National Academy of Sciences Polar Research Board, I think. Then I saw the plan and I said, hey, I don't like this at all. You've neglected a very important part of the Earth system, and that's ice. And so the Academy convened a committee, and because I had opened my mouth on this matter, guess who got put on the committee? It was headed by Jack Eddy, sometimes called the Eddy Committee, that fought over what should be the composition of this program, what fields of science should be represented, what should be the underlying scope and theme, or as John Eddy would say, the catechism. How should we limit it? It can't just be all science forever. And we fought long and hard battles, and those committee meetings I will never forget, because some of them were pretty brutal. We decided to exclude the geologists who worried about million-year time scales. We decided to exclude the astronomers and things that were so far, their subject matters were so far away that they had no impact to speak of on society on a 100-year time scale. And we defined a program and wrote it up as the U.S. Global Change Effort, an initiative for international Geosphere Biosphere program. That then was taken to an international meeting, and the International Geosphere Biosphere program came into existence. But it was very much the American template that was then used internationally to develop the main program. So having been a part of that process, I feel very proud, and I've been very much energized by these new opportunities to do interdisciplinary work on the total Earth system, which has biology in it, and has water in it, and has atmosphere in it, and has land in it, has ice in it, and it has chemicals, and it has all sorts of things.
It's interesting, you started off on the Saskatchewan Glacier on a very specific and, if you like, a little personal project, very well defined probably, and very feasible. And only you, plus your helpers and so on, involved. Then you were getting into, maybe 10, 15 years later, into international hydrological programs, let's say specific to hydrology, containing a glacier component. And now you're into very much broader interdisciplinary subjects. Now, you mentioned the Geosphere Biosphere program. I mean, who runs this thing? Perhaps you can give us perhaps you can give us a bit of your insight onto how on earth you bring scientists from different disciplines together. Under what sort of umbrella is this done, and is it done successfully?
It's not without its difficulties. First of all, there's a built-in bias against interdisciplinary research. And the bias extends from the fact that each of us at our own undergraduate and our graduate training in some particular discipline, which is very important. But it doesn't stop there. Each of us, or many of us at least, go to funding agencies to get money to support our research. The funding agencies are arranged by disciplines. They have disciplinary pigeonholes. They have review teams out of that one discipline. If you say you want to do these things in many different programs, they don't know what to do with your application.
That's right.
If you are in academia, if you get a job as a tenure-track assistant professor, you are not evaluated on your total contribution to science. You're evaluated on what did you do for us in our department,
Yes.
which is a very disciplinary view. Yes.
Yeah.
And so there are a lot of obstacles. What
Natural obstacles.
what I have noticed and what I would like to bring to the attention of as many people as possible is that you should do everything you can to break out of that without endangering your career, because each discipline is so well entrenched and has done work in such depth that it's pretty hard to,
With a narrow focus.
with a narrow focus, to go beyond. Whereas in between the disciplines, there are these great big gaps of knowledge just waiting to be filled.
Yes.
Wonderful research opportunities.
Yes, that's right.
And so if you are, for instance, a geologist who also understands biology
Yes.
very well, you have lots of opportunities that just straight geologists don't
Yes.
have.
Yes, that's right. On that, I remember, I think it was about 1978, there was, in Canada, there was a very interesting little conference bringing together glaciologists who looked at present-day glaciers and how they move and how they act, and glacial geologists who essentially had been looking at the effects of glaciation but not really considering the glacial processes. And the bringing together of those two sets of people who had tended to stay apart
Even
because
though
they
they're
were
really
focused.
only in one subset of
Really
their
only,
sciences. Yeah.
Bringing those together
Yeah.
brought out a whole lot of very stimulating discussion, and it was very, very beneficial. And what you're saying on a much grander scale is that many disciplines can be brought to bear, and along the intersection of disciplines there are extremely interesting areas, very, very valuable areas of research.
That's why I'm really excited about the American Geophysical Union in my country and the International Union of Geodesy and Geophysics internationally, being an earth scientist,
Yeah.
basically.
Yeah.
Because I can go to an annual meeting or a quadrennial meeting of one of these groups, and I can go and sit in on the seismologists
Yes.
and learn how to approach the sliding of a glacier on its bed. And I can go to the oceanographers and learn something about ocean currents as they might be affecting calving. And I can go to the meteorological associations and learn about things that apply directly to my problems, and sometimes I can help them a little bit too.
That's
And I think that's very stimulating.
Yes, and I guess that's one of the reasons why we and the 4,000 others who have been here in the last
Yes.
couple of weeks come to such large meetings,
Yes,
because
yes.
it gives us the opportunity not only to listen to detailed talks on our own particular, let's say, narrow interests, but also to listen to very stimulating discussions and talks and lectures in related or unrelated subjects, but which are related in the sense that they stimulate our thinking and make us think more broadly.
I think, as I look back on my career, the few original contributions that I have made, I think have largely been stimulated by work that I've been exposed to totally outside of my field.
So as a teacher, as a professor, you would probably encourage students to have to open their eyes and to look sideways as well as forwards. Do you think the students in their basic training are brought up with that kind of broad perspective, or?
No, that's a problem. Well, first of all, it's very important if someone is going to go into science, especially pure science or academic science, that you do have a very deep understanding of some field. That's your union card, your ticket to scientific credibility.
Yes.
If you're going to be a geologist, you know, you've got to have a pretty good deep knowledge of basic geology.
Yes.
But I would emphasize that the most important courses that you need are the ones that are the most basic sciences.
Yeah.
You should be well-rounded in mathematics, physics, chemistry, perhaps biology, if you're thinking along those lines, and not worry so much about the very specialized courses, except where they're needed to get that dissertation finished or whatever. And to always, as you say, keep your eyes open to other fields.
Yeah.
Obviously, you can't study everything,
No.
but keep your eyes open.
Yes.
And have the basics down. That's the
Yeah.
most important thing.
So the eminent scientist of the future, who is now studying for an undergraduate degree, should be paying attention to the basic sciences, and then perhaps gaining a knowledge at perhaps the graduate level, a master's degree or a PhD, an in-depth study.
Yes, yes.
Is it? Would you advocate at that level as having a broad sweep, or would you still advocate for most people? It's difficult to generalize, I guess, and
Yes.
say what's right and wrong for everybody. But at the master's and PhD level, should they be doing an in-depth study or
Yes.
something broader?
You have to. This is not a perfect world. And the young person has to establish his or her scientific credibility right off the bat. And the way to do that is to make a good, deep research contribution, which means that that's a fairly narrow experience that you have to undergo. But I think that should be done. You should concentrate on that in graduate school, not before. I am often approached by people who say, I'm just starting college and I want to be a glaciologist.
Yes.
How do I study glaciology in undergraduate school?
Yeah.
And I say, forget it. Study physics and mathematics and so forth. And if you're interested in glaciology, you can pick up the specialized courses in
Later.
graduate school at a
Yes.
later time.
Yes.
Meanwhile, you're in a much better position because you don't know if there will be a field of glaciology, for instance, or anything else, or a job. Everything is changing so much, but if you have the basic skills, you're better prepared. If you're narrowly specialized, that
Yeah,
particular
beware.
field you're specialized in could evaporate, and
Yes.
you're out of luck.
Yes, yes. Well, I guess we could go along the educational discussion for an awful long time, but that might be a little long-winded and take
Yeah.
us away from your personal contribution to science. Are you able to look into the near future or into the slightly more distant future and say what you hope to be doing in the next little while in a research fashion?
Right now, my personal research is largely involved in the sea level question. In other words, trying to look at the impact of ice wastage on sea level change, which relates, of course, to climate change in many aspects. And so what I'm doing is I'm trying to apply some new techniques of scaling, you might call it fractal analysis, to try to get some knowledge about this huge spectrum of sizes and numbers of glaciers around the world and how they behave, and how to combine both their response to climate change and their own internal dynamic response to that, which changes their area, which is subject to melting and so on. There's enough of a problem there to keep me occupied for a long time.
Well, Mark, I hope I hope it does keep you occupied and productive as you have been over these many years into the future. And I shall certainly, as I always have been, looking to see what you're doing and getting inspiration from your work. I'd like to thank you very much indeed for this opportunity to talk to you.
Thank you, Gordon. I enjoyed this, yes.